This video is for Stat 110, Module 4, Part 3, and includes a discussion of measures of association for tables. Okay, let's go ahead and get started then. So for this section here, we are going to be using the Donner Party dataset. The Donner Party was a group of American pioneers who set out for California in a wagon train. Delayed by a series of mishaps, they ended up spending the winter in the late 1840s, snowbound in the Sierra Nevadas. Many in the party did not survive the harsh winter in the mountains. So here is a view of the Donner Party dataset. You can download that here, and I've also included the wiki link to the Donner Party. The primary variable that I'm going to be concerned about is survived. So that's going to be my response variable. The predictive variable that I'm going to be using in this example is gender. I can create my pivot table in a spreadsheet, again specifying survived as my response variable, gender as my predictor variable, and because each individual, so this data set contains information about each individual, my summary is going to be a count. I also can place survived in the filter box and deselect blanks so that I don't contain information about the blank rows. So the term risk refers to the negative level of a response variable. So here my survived has two levels, it's no or yes. So if I was referring to the no survived, if they did not survive, I would identify that as the risk of death. If I'm talking about those that did survive, I could refer to that as the rate of survival. So the risk is often used to refer to the negative outcome of the response. So here's a table of counts and row percentages for the Donner Party dataset, and also the mosaic plot that was created, or 100% stacked column graph that was created for that data. We're going to be working concentrated on the risk of death between females and males. So you can see that males were much more likely to have died than females in the Donner Party. 58% compared to 26%. Okay, so when we're wanting to make comparisons in those two risk levels, we can do one of two things. We can look at the risk difference, or we can look at the risk ratios. Now, before getting into those discussions, let's just consider the following comparison in the amount of cash between, say, you and I. So suppose that you have $40 in cash, and I only have $20 in cash. There are two different ways that we can talk about how much more money you have than me. The first and the simplest is to look at the difference. So if you have $40 and I have $20, then you're going to have $20 more than myself. So we would just say that you have $20 more than me. When we do a ratio, what we're going to do is take the $40 and divide by the $20. And when I do that, I get a value of 2. The interpretation of this quantity is that you have twice as much money as me. Now the units, which in this case are dollars, are retained for a difference. So when I'm looking at this difference, that's $20 difference. However, they are not retained when using a ratio. So a ratio here is twice as much money as me. This is not $2 more money than me. There are not units attached to the ratio here, so we often refer to that as a unitless measure. Those two same ideas can be used when we talk about risk. We can either look at the difference in the risk or the ratio in the risk. So let's go ahead and compute the difference in the risk. So the difference in the risk of death is going to be the risk of death for males minus the risk of death for females. So I would just take that 58%, which was the risk of death for males, and subtract 26.5%. That difference is 31.7%. The interpretation here is that the risk of death for males is a little over 30% higher than the risk of death for females. Or if we wanted to be exact, I would say the risk of death for males is 31.7% higher than the risk of death for females. Quite simply, the risk difference is just the difference in the heights of these two boxes. It turns out that if these two boxes were the same height, when I subtract them from each other, I would get 0. So if I got a risk difference value near 0, then that would say that the risk is not that different between females and males. I could compute the difference in the risk, which was that 31%. Now that's going to be the same as the difference in the survival rates. So it doesn't matter if you are subtracting the heights of the two gray boxes or the heights of the two black boxes, you're going to end up with the same value. That's not the case when you do risk ratios. Now, one thing about this difference in risk is it does not retain information regarding the original level of risk. So, for example, consider the following situations here. Situation A, where most of the people survived. You can see that I have a 5% difference in risk, with males being higher again. In this situation over here, situation B, I have most of the individuals have died. Again, there's a 5% difference in risk. So when I report the difference in risk, it's going to be 5% for both situation A and situation B. And what I mean by this comment is it does not retain information regarding the original level. So you have no idea if most of the people survived or if most of the people died. You just know that there's a 5% difference between the males and the females. So that's one caveat about looking at the difference, is it does not retain information about the original level. How about a risk ratio? So what a risk ratio is going to do is it's going to take the height, or take the ratio of the 58.2 and the 26.5. And when I do that math, I end up with 2.2. The interpretation of this quantity is that the risk of death for males is 2.2 times higher than the risk of death for females. So when I do my interpretation with the ratio, the risk of death for males is what sits in the numerator of this ratio, and that is 2.2 times higher than whatever is sitting in the denominator of that ratio, which would be the risk of death for females. What does that mean visually? Well, it means that it is going to take 2.2 of these female boxes to reach the height of the males. So I have one here at 26.5. I need another 26.5, which is going to get me up to about 52% or so. And then I need a little bit more to get up to that 58%. So I need 2.2 of the female boxes to reach the height of the male box here. As I said above, the risk ratio is not a percent. The ratio is a unitless measure. A relative risk ratio of 1 implies that there's no difference in the risk. So if, for example, if it was 38.4 on the male and 38.4 on the female, when I look at the ratio there, it's going to be 1. So there's a difference. When I'm talking about the differences, no difference in the risk is going to be 0 is my baseline value. But no difference in risk when I'm looking at a ratio is going to be 1. So values near 1 are going to imply no difference in risk, and values far away from 1 would imply that there is a difference in risk. Again, the risk ratio does not retain information regarding the original level of risk, so that's just like the risk difference. The risk ratio for death is not the same quantity as the risk ratio for the survival rates. So when we're talking about ratios, we need to identify, are you talking about deaths or are you talking about survival rates? A small relative risk ratio, again, is going to be near 1, as I just mentioned. Turns out that a risk ratio cannot go below 0, and it doesn't have any upper limit as well. Sometimes the risk ratio is actually converted backwards, or the inverse. So if I would have computed the risk ratio of females to males, then I would just turn around what I put in the numerator and denominator, and I'd end up with a value of 0.455. Now the 0.455 actually means that the risk is lower for females because it's less than 1. The interpretation, though, would have to be the risk of death for females is about 0.455 times higher than the risk of death for males. Now that gets a little bit confusing because it's actually lower. One way that we alleviate this confusion is just to compute the relative risk ratio so that it's bigger than 1. This is much easier to interpret when the relative risk ratio is larger than 1. If it has been computed so that it's less than 1, you can just flip it around and then it would be easier to interpret. Okay, finally, odds ratios. Now, odds ratios are a direct comparison of the values or the counts and are not based on row percentages. So here is just a cash in a flash. It's a lottery game that's from the state of Wisconsin, looks like. The odds of me winning $2 are 1 to 8. So I'm going to win once and I'm going to lose every 8 times. If we wanted to compute the chance of me winning, it would not be 1 out of 8, but it would actually be 1 out of 9. So the total number here is 9. That's one thing that's confusing about odds is some people think it's just the same as percents or chance of winning, and that's not the case. So the chance of winning, if I were to compute that for this lottery, the chance of winning $2 is going to be 1/9, or about 11%. Now let us reconsider the table of counts for the Donner Party data set. If I do a direct comparison of the counts, then I'm not going to use these totals. So I'm just going to do a straight comparison of the 9 to the 25 for females. And we would refer to that as the odds of death for females. So the odds of death for females would be just 9 to 25. And what that means is that 9 women died for every 25 that survived. Now the odds of death for males are going to be 32:23. So more males died than survived. So the odds ratio is going to be a comparison of what's going on for the females compared to what's going on with the males in terms of odds. Again, we're going to want to compute this so that it's bigger than 1. So I'm going to look at the odds of death for males, which are going to be 32:23. And that's going to be relative to the odds of death for females, which is going to be 9:25. Now we pull just a sleight of hand there because I cannot do this ratio with a colon there. So I actually take 32 divided by 23. So I express that as a ratio as well. And then the 9 divided by 25. So an odds ratio is actually the ratio of ratios, which gets to be a little confusing, and it's somewhat more difficult to talk about. So the odds ratio here, doing the math, is about 3.86. So when I'm interpreting odds ratios, I need to do those in the context of odds. So the interpretation here would be the odds of death for males are about 4 times higher than the odds of death for females. I cannot change this or say that the rate of death for males is 4 times higher than the rate of death for females. If we use the word rate, then it's assumed that we're talking about relative risk ratios. So when I'm interpreting odds ratios, I need to interpret those in terms of odds. Again, this is a ratio, so a small odds ratio is going to be near 1, whereas a large odds ratio would be far away from 1. Odds do not use the totals. Okay, so when I did my odd comparison here, I'm looking at these numbers directly compared to these. I'm not using the totals at all when I'm computing an odds ratio. And what that means is they can be used in studies where the totals have been predetermined by design. So for example, suppose a study is designed such that 250 are put into each group. Here the totals have been predetermined. And the calculations that use the row totals should not be used. We can't set those totals and then use those in calculations. But you can do odds ratios. So in studies where you have predetermined the number of people in each group, it's much more common to use odds ratios to make comparisons. In both of these situations, the odds ratios are going to be 1 because the relationship between females and males has not changed. So here that ratio is going to be 1, and also on the right the ratio is going to be 1. The number of people doubled for the male group, but it also, in the not survived group, but it also doubled in the survived group. So the odds ratio here is going to be 1. Okay, here's just a bunch of questions, true-false questions about your understanding of risk differences, risk ratios, and odds ratios. Okay, that does it then for Module 4, Part 3, Measures of Association for Tables. Thank you.